this video, we will be looking at the first part of the preparation of haloalkanes that we're going to call halogenation of alkanes. So if you remember, we talked about 4 ways in which haloalkanes are prepared. One of them is from alkanes by halogenation. You replace a hydrogen with a bromine. Well, that reaction is complicated enough that we're actually going to do it in 2 videos. So the first part is predicting products, and then in the second part, which will be CH07.04b, we will talk about the mechanism of the reaction. But first we need to learn the reaction and learn how to predict the products of the reaction. So please read section 8.4, just the introductory part, and part A, that's on pages 292 to 294 in your textbook. So here's the overall reaction. Alkanes react with bromine and chlorine, that's the element bromine, Br2, or the element chlorine, Cl2, to give a haloalkane, and also produces HBr or HCl. So here's the overall reaction, starting with an alkane, and this is just an alkyl group with a hydrogen, so this is an alkane. Reacts with the halogen molecule, the X2, that's Br2 or Cl2. You always have to put in a little bit of heat or light to get the reaction started, and then 1 hydrogen on each molecule gets replaced to produce an alkyl halide. Notice that the R group that you start with here is the same as the R group that you end up with here. No rearrangements in the reaction. And if you want to balance the equation, then you have the hydrogen and the extra halogen that come off as HCl or HBr. Typically this is not done in water, so the HCl or the HBr is a gas and it just evaporates out of the mixture. So it seems easy enough, right? So let's look at an example. So here's the simplest case, just plain old methane, CH4 plus Br2 gives, as you would predict, CH3Br, so methyl bromide, by replacing one of the 4 hydrogens with a bromine. And of course you get HBr as a byproduct. I've shorthanded the heat or light, so delta stands for heat, the H nu stands for light, so that's a photon of light. Or you can just write it as the starting material, in this case CH4 with bromine over the arrow, and gives you methyl bromide. Now, there's a critical thinking question. You might want to review video CH07.05, which was called Once or Twice. That gives you a hint. So what question would arise from just this reaction with methane itself? Here's the question. Can halogenation happen again? So if you replace one of the hydrogens with a bromine to get CH3Br, can you then react it with another equivalent of bromine, replace another hydrogen with another Br, and get CH2Br2? And furthermore, can you do it yet again and replace the 3rd hydrogen with bromine to get CHBr3? And then finally, could you replace the last remaining hydrogen with a bromine to get CBr4? By the way, this is methyl bromide or bromomethane by name. This is dibromomethane, sometimes called methylene bromide. This is bromoform, which is analogous to chloroform. If those were chlorines instead, that would be chloroform. And this is carbon tetrabromide. So what's the answer? Can it happen again? Does it happen faster the 2nd time, and possibly the 3rd time, and so on? Or does it happen slower, in which case you can stop it after the 1st time if you want? Well, the answer is it's complicated. You do tend to get some over-halogenation. You can control it by limiting it to monohalogenation by putting in a big excess of the alkane, but then of course you get terrible yields. But you can get monohalogenation if you want to, and so that's what we're going to do throughout the rest of the chapter. We're going to deal with monobromination or monochlorination only, but keep in mind that it actually in real life does go on to produce some dihalogenation and trihalogenation and so on. Okay, so let's look at another example. So here is ethane, and if we react it with Cl2, I've switched to chlorine instead of bromine, same idea, and put in a little bit of heat or light, we will get ethyl chloride plus HCl as a byproduct. The main thing is you replace one of the 6 hydrogens with a chlorine, and that's simple enough because all 6 hydrogens are the same as each other, as they are in the case of CH4. Obviously, all 4 hydrogens are the same as each other, so that makes it easy. But what if the alkane has more than one kind of hydrogen? For example, the next alkane on the list would be propane, CH3, CH2, CH3. So the question is, how many kinds of hydrogen are there here? So look carefully and say how many kinds of hydrogens. Actually, it's pretty easy in this case. Obviously, there's a CH3 and another CH3. Those turn out to be the same as each other, and so all 6 of those hydrogens are the same. Clearly, the CH2 is different, so those 2 hydrogens are different. And I've highlighted that with just using a little bit of color here. So the red ones are the same as each other, and the blue ones are different from the red ones, obviously. So 2 kinds. I've labeled them as A for the methyls and B for the CH2. What about butane, the next one on the list? So 4 carbons hydrogens in a straight line. How many kinds of hydrogens there? And the answer is, again, 2 kinds. So the CH3s on the ends are the same as each other, and the CH2s in the middle are the same as each other. So again, we have 2 kinds. I've labeled them as A, B, and A. So the CH3s are A and the CH2s are B. So it seems easy enough, right? Well, let's throw a monkey wrench in. So here's pentane. So how many kinds of hydrogens in pentane? Well, now we have a question. Clearly the CH3s are the same as each other, so that's one kind. And the CH2s are not the same as the CH3s, so that's another kind, right? Well, here's a question. Is that kind of CH2 the same as that kind of CH2? And the answer is no, because this CH2 is between 2 other CH2s, whereas this kind is not between 2 other CH2s. It's between a CH3 and a CH2. So this kind is different from this kind. In fact, in this particular molecule, that CH2 and that CH2 are the same as each other. The CH3s are the same as each other, but that CH2 is different. So notice 3 kinds in this case. The methyls are the same as each other, so those 6 hydrogens are all the same. These 4 hydrogens are all the same, so that CH2 and that CH2 are the same, but the CH2 in the middle is different. So literally 3 kinds of hydrogens here, so A, B, and C. What about in this molecule? It's a little more complicated. How many kinds of hydrogens altogether here? Well, the first question is, are the CH3s all the same as each other? Well, these 2 are the same as each other because they're both on the same carbon, so all 6 hydrogens are interchangeable. They're all the same as each other. But that's different from this kind of CH3. So these hydrogens are different from these hydrogens. So there's 6 the same here, and 3 over here that's not the same. So why are these not the same? Because this CH3 is attached to a CH2 group, whereas this CH3 is attached to a CH group, so clearly not in the same environment. What about the CH2 groups? Are they the same as each other or not? And the answer is, again, clearly no, because this CH2 is attached to an isopropyl group, this CH2 is attached to a methyl group, and so the 2 different CH2s are different from each other. So how many altogether? And the answer is 5 kinds. So this CH3, these 2 CH3s, the CH2s are different from each other, and then of course the CH is different from all the other ones. So I've labeled them as A, B, C, D, and then these 6 are all the same as each other, and so that's E. So a total of 5 kinds of hydrogens in that case. So why are we worried about kinds of hydrogens? Well, it turns out for each kind of hydrogen, you will get a different alkyl halide if you replace it with a halogen. So what is the product of monochlorination? Again, I'm limiting it to just 1 chlorine going on. Monochlorination of propane. So look at this molecule and decide how many possible products would you get here and what would their structures be. So stop the video if you haven't already done so and write down what you think you would get from propane. Just to review, there's propane right there. Okay, so what's the answer? The answer is 2 different products. As I said before, since there were 2 different kinds of hydrogens, we will get 2 different products from it. And I think that's fairly simple to see in this case. The CH3s, if you replace any one of those 6, you will get 1 bromopropane. If you replace one on this end, it would be the same thing as this, just turned backwards. But if you replace one of the hydrogens in the middle, that would be different, and that would give you this product. So this would be 1 bromopropane. This would be 2 bromopropane, or isopropyl bromide and N-propyl bromide. 2 different kinds of hydrogens, 2 different possible products from monohalogenation. What about butane? Well, we said there was 2 kinds of hydrogens there. The kind I've labeled as A and the kind I've labeled as B. And so we would expect chlorination to give 2 possible products. One where the chlorine attaches to one of the end carbons, that would be N-butyl chloride or 1-chlorobutane. If the chlorine attached or substituted on one of the hydrogens in the middle, you would get 2-chlorobutane or sec-butyl chloride. So again, 2 kinds of hydrogens, 2 possible products. What about N-pentane? Well, remember we had 3 different kinds of hydrogens here. So the 6 on the end, that would give you 1 bromopentane. These CH2s that I've labeled as B in this case, that would give you 2 bromopentane. And the kind in the middle is different from the other ones. I've labeled it as C here. That would give you 3 bromopentane. So 3 kinds of hydrogens, 3 possible monobromination products in this case. Now let's look at this more complicated one. Remember we had 5 kinds of hydrogens? Well, indeed we have 5 different products. So we could replace that kind of hydrogen, that kind of hydrogen, that kind of hydrogen, that kind of which there's only 1. And then these 6 are all the same as each other, so that would give the same product. So notice we have 1-chloro 4-methyl pentane, 2-chloro 2-methyl-3-chloropentane, 2-chloro-2-methylpentane, and 1-chloro-2-methylpentane. Those are all different from each other. They have different IUPAC names, and obviously they come from 5 different kinds of hydrogens being replaced. Okay, so we got all these different possible products. Which one would we get more of than the others? Is one of them preferred to the others or not? Can we say, well, this one is the major product or this one is the major product? Well, in the case of monohalogenation, we can actually calculate roughly what percentage of each of the products there would be. Well, let's go back to the propane case. We saw there were 2 kinds of hydrogens. There's 6 of this kind that I've labeled as A, and only 2 of that kind that I've labeled as B. So you would guess that maybe you would get 6-to-2 ratio of product A and product B, because there's 6 hydrogens that could be replaced to give you A, but only 2 hydrogens that could be replaced to give you product B. And that's in fact one of the 2 factors. It's called the statistical factor, and it's simply due to the number of each kind of hydrogen that you're starting with. So it would be 6-to-2 because you're looking at the starting material. But it turns out that's not the only factor. It turns out also that tertiaries are more reactive than secondaries, which are more reactive than primaries. A little bit in the case of chlorine, a lot in the case of bromine. So there's actually 2 different factors, one called the statistical factor and one called the energy factor. Well, it turns out that the statistical factor, you just count the kinds of hydrogens, or the hydrogens of each kind, so 6-to-2. So in this particular case, the statistical factor would be 6-to-2. But what about the energy factor? Well, as I said, in the case of chlorine, there's a preference for tertiary over secondary and secondary over primary. Turns out that preference is roughly 5-to-4-to-1, so not a big difference between tertiary and secondary. Kind of a big difference, but not all that big a difference between secondary and primary. But for bromine, for whatever reason, bromine is way more selective, means it way prefers tertiary hydrogens over secondary hydrogens and way prefers secondary over primary, to the point that the ratio has been determined to be roughly 1600 for tertiary to 80 for secondary to 1. So it's a big difference between those in the case of bromine. And so then to get the overall ratio, you just multiply the statistical factor times the energy factor for each kind of hydrogen. Let's do an example. So for propane, notice, as I said, the statistical factor is 6-to-2 for compound A to compound B. 6-to-2, and that's just the number of hydrogens of each kind. The energy factor for bromine, since we're doing bromination here, is 80-to-1 in favor of secondary. So since B is secondary and A is primary, the energy factor is 80-to-1. So we multiply those 2 factors together. That gives you 6 for compound A and 160 for compound B. You can see that compound B is going to be way favored because bromine so much prefers secondary. Even though there's more primary hydrogens, the secondary ones are way preferred, and so you're going to get the secondary product in large part. So you figure out the percentages the same way we've figured out percentages of lots of other things. Add up the 2 numbers, gives you 166. Take each of the individual numbers divided by the total, which is 166. So 6 divided by 166 gives you roughly 4%. 160 divided by 166 gives you roughly 96%. Now these are really rough numbers. This is only an approximation, but it does tell you that the isopropyl bromide would be favored over the N-propyl bromide by a ratio of essentially 96-to-4. So for all intents and purposes, you can say that this is going to be the only product form. There will be a little bit of this, but for the most part, it'll be that product. Let's look at the butane case. Again, we had 2 kinds of hydrogens, primary and secondary, 6 of this kind, 4 of this kind, so the statistical factor is 6-to-4 in favor of A, because there are more primary hydrogens than secondary hydrogens. But because this is chlorine, not bromine, the energy factor is 4-to-1, secondary favored over primary. So not a big difference here. 6 times 1 is 6, 4 times 4 is 16, total is 22, 6 divided by 22 is 27% for the A molecule and 73% for the B molecule. So roughly 75 to 25%, roughly 3-to-1 in favor of this product over that product. And that's in large part due to the fact that the energy factor is bigger for secondaries than it is for primaries. That would not be a particularly useful synthesis if you wanted to make this compound, because you only get it in roughly 75%, and plus the fact that you have this other one in there that you got to somehow get rid of, and the properties are probably pretty similar, so it's going to be hard to distill them apart, or some other method to get them separated from each other. If you wanted to make this product, it would be a terrible way of doing it, because because you're only going to get about 27% of this, and the vast majority of it's going to be the one that you don't want. So chlorination, usually not a good synthesis, although there are exceptions, and we'll go over those at the end. Okay, now let's go to the pentane molecule. Again, we saw that there are three kinds of hydrogens here, the 6 on the end, the 2 on these CH2 groups, and then the CH2 in the middle, so A, B, and C. Here's product A, here's product B, here's product C. Again, statistical factor is going to be 6 to 4 to 2, because there are 6 hydrogens of type A, 4 hydrogens of type B, and 2 hydrogens of type C, so 6 to 4 to 2. The energy factor is going to be 1 to 80 to 80, and that's because these are primary hydrogens, these are secondary, and those are also secondary. So if we multiply out the factors, we get 6 to 320 to 160, total 486. 6 divided by 486 is 1%, so you only get 1% of this product over here, and that's because it's primary. You get roughly 66% of this one and roughly 33% of this one. So about 2 to 1 in favor of this. Again, not particularly good for synthesis because you're getting a mixture of things with significant amounts of both. Now let's look at this one. If we do chlorination for this one, the statistical factors are 3 for type A, 2 for type B, 2 for type C, 1 for type D, and 6 for type E. And energy factors 1 for A and E, because those are both primary, to 4 for type B and C, because those are both secondary, and 5 for type D, because it's tertiary. So multiplying out the statistical times the energy factors, you get 3 to 8 to 8 to 5 to 6. And adding those up, you get 60. Dividing them out, you're going to get roughly 10% of A, 27% of B, 27% of C, 17% of D, and 20% of E. And so those, you get a terrible, horrible mixture, none of them more than roughly 25%, and you got 5 different things in there that you got to separate from each other. So that would be a horrible synthesis if you wanted to make any one of those 5 things. But what if we did the same problem with bromine? Again, the statistical factors are the same, 3 to 2 to 2 to 1 to 6, because 3 of that type, 2 of that type, 2 of that type, 1 of that type, and 6 of that type. The energy factors are going to be 1 to 80 to 80 to 1600 to 1, because that's primary, secondary, secondary, tertiary, and then these are also primary. Multiplying out the factors, 3 to 160 to 160 to 1600 to 6, that adds up to 1929. Dividing it out, you get way less than 1% of A, and that's, again, primarily because it's primary, and you get very little primary with bromination. About 8% of B and C, again, less than 1% of E, but fully 80-some% of D. And so if you wanted to make this compound, it would probably be acceptable to try to do it this way, although it wouldn't be the greatest because you still got all these other compounds in there that you got to get rid of, separate them out somehow, and even at that you're only getting 80-some% yield, which would be acceptable, but not, again, not the best. But notice that if there's a tertiary hydrogen with bromination, the tertiary product will way outstrip the rest of the possible products, and any secondaries will way outstrip any primaries that you might get. So let's just do one more thing. If I gave you an alkane, could you tell me how many possible products you would get? And specifically, are there any alkanes that would give you essentially just one product, essentially 100% of a monochlorination product? So looking at these 7 molecules that I picked out here, which of them do you think would give you just one possible monochlorination product? So take a few minutes and look those over and see how many products would each give you, and are any of them such that you just get one product. If you only get one product, then you can probably use it in synthesis because there are no byproducts. You get essentially 100% yield of the one that you want. Okay, this one would give you just one possible product because it turns out all 12 hydrogens on those 6 carbons are the same as each other. So you would just get chlorocyclohexane as your monochlorination product. That would be a fine synthesis. What about this one? Well, there's all sorts of different kinds of hydrogens now. The only difference is there's a methyl there. So there's 3 hydrogens on that methyl. There's 1 tertiary one here. Then these 4 on these 2 carbons would be the same as each other, but different from these 4 because they're in a different position relative to the methyl group, and those will be different, of course, than these over here. So there's actually going to be 1, 2, 3, 4, 5 possible products. You'll get a big mess, and this would not be good for synthesis. Now, if you did bromination instead, you would probably get a pretty good yield of the one product where the bromine would attach on there, because that's the only tertiary carbon in the molecule, but still not 100%. yield. What about methane? Well, we already saw earlier in this lecture that only has one kind of hydrogen and just gives you one possible monochlorination product, so that would be fine for synthesis. Ethane we saw earlier, all 6 hydrogens are the same as each other, so again, only one kind of monochlorination product, and therefore that would be good for synthesis. What about propane? Well, we saw that it has 2 kinds of hydrogens. Not good if you're using chlorine, because you get roughly equal amounts of the 2 possible products. Bromination probably would be okay, because as we saw, you get like 96% of the secondary and only 4% of the primary. What about isobutane or 2-methyl propane? Would you get just one possible product there? And the answer is no, because these 9 would all be the same as each other, but that one would be different. So you would get 2 possible products. Again, with bromination, it would probably be acceptable to do if you wanted to get the one where the bromine was there. But if you wanted to get the one where the bromine was out here, that would not work. What about this one called neopentane, otherwise called 2,2-dimethyl propane? Well, notice that that has 12 hydrogens, but they're all the same as each other. So that one would just give you one possible monohalogenation product. So that would be fine in synthesis, either chlorine or bromine. And that's the end of this talk. Thank you.